Hi, good afternoon. We are Los Ciclistas presenting our project Cruise Control Exhibition Tricycles with the professors Raúl Torres and Naida Santiago. Our team is composed by Ángel Colón Rios, the project manager, Cristian Falero González, Cristian Ramírez Gómez, and Samuel González Ortiz. Our presentation is divided in the problem statement, proposed solution, objectives, budget, a video demonstration, and conclusion.
During the last 5 years, only 13% of new applicants have selected electrical or computer engineering as their major. This is a low amount when compared to previous years. Our proposed solution consists of developing a cruise control system for an exhibition tricycle to be used in outreach events. This will be done with the purpose of inspiring middle and high school students to study electrical or computer engineering at the UPRM.
The objectives are as follows. Measure speed, battery charge, and current consumption. Display battery gauge and current speed on board. Functions in the range of 3 miles per hour to 7 miles per hour. Increments and decrements in 1 miles per hour steps while activated. Wirelessly transmits data to be displayed on a web page. Completed the budget under 600. The proposed cost for this project was approximately $25,000 in human resources, $129,000 in equipment, $515,000 in materials, and $13,000 in overhead for a total of $39,000. The actual cost of the project was $27,000 in human resources due to the fact that the project was extended an additional week, $630 in equipment due to the fact that the team acquired 4 licenses of MATLAB for each team member instead of only 1 as proposed initially. The cost of material was $496, which was actually under budget since the batteries were provided, and $50,000 in overhead for a total of $43,000.
The microcontroller used for this project was a Raspberry Pi 4, which we programmed using Python 3.7. It is in charge of controlling the motor, presenting data on a graphical user interface, and transmitting the data to be presented on the web page. For better functionality of the system, the code was developed using multi-threading, with threads focused on a specific task. Communication was made by using WebSockets to provide real-time updates for the web page. This is an oversimplified view of the system flowchart to help demonstrate the usefulness of threading. The orange blocks form part of the main thread. As you can see, once it reaches the display instruction, the code is stuck on an infinite loop to update the graphical user interface. By using multiple threads, we are able to keep the system operating normally, even while the main thread is stuck updating the display. The data sent from the microcontroller is received by the server and emitted to the client. The client side is implemented using HTML, CSS, and JavaScript, with Bootstrap and other libraries used for styling. The server side is implemented using Node.js, or more specifically, the Express variant of Node.js.
A PCB was designed using Autodesk Ego to better accommodate all the electric components and to reduce the possibility of short and open circuits.
An enclosure was designed to protect the electronic components and organize them at the same time. Also, a translucent lid was implemented to generate a greater appeal for the targeted audience. At the left can be observed the CAD design and in the right the manufactured product.
Using MATLAB and Simulink, we were able to construct a model for our system. The Simulink block diagram is shown. Here we can see the model is divided into 3 blocks: input, MCU, and plant. The MCU is where the controller is located. The plant represents the tricycle motor system. To obtain this controller, first the plant had to be determined. To do this, MATLAB's System Identification Toolbox was used. After arriving at a consensus of the system's plant, MATLAB's RL tool was used accompanied by the PID tuning feature. After various controllers were tested, a PI discrete controller with a gain of 0.15 and a 0 of 0.991 was utilized. With this controller, a settling time of around 12 seconds and an overshoot of 8% was obtained. The results from the simulation and the physical test are shown respectively. The blue lines are the set speed in miles per hour, and the orange curves are the output miles per hour. Here is a demonstration of the system operating with the rear wheel lifted. This is recognized as the static configuration. Here is a demonstration of the activated cruise control. Here can be seen the graphical user interface and the web page at work. Seen here is a demonstration of the kill switch that was implemented for safety purposes. A message will be displayed and the system will not run until the kill switch is released.
Finally, the design controller fulfills the established objectives. Also, the web page is currently live and plotting data in real time. The project was complete with the established budget thanks to the funding of the Industrial Affiliate Program. Also, several safety measures have been implemented to greatly reduce the amount of risk incurred by the user. Working in this project has been an enriching experience that has allowed the team to put into practice a wide variety of skills learned through the years. These are the references used for this presentation. We want to thank you all for attending this presentation, and now we are going to pass to the question session.